So we'll solve one or two problems on the discussed concept. So first problem, it is problem 2.3 from BC Punmiya book, which I shared you yesterday through Google Classroom. Okay, BC Punmiya Strength of Materials. So I'm just writing down a rod of variable sections shown in figure is subjected to a pull of 100 kilonewtons at the ends. Find the extension of the rod. Find the extension of the rod. So taking Young's modulus as 2 into 10 power 5 Newton per mm square. Now this is the figure. So there is a 1000 kilonewtons applied this side, and this side also 1000 kilonewtons. Okay, and here it is 100 mm, all are in mm. 100 mm is the diameter of the rod. Circular cross section is there, and this is 70, and this is 90, and this is 70, and this is 100, and the lengths are 0.6 meters, 0.4, all are in meters, 0.5, 0.4, and 0.6. Now see, what you have to find out is a rod of variable cross section. So it is having different cross sections. It is subjected to 1000 kilonewtons at the ends. Find the extension of the rod taking Young's modulus equal to 2 into 10 power 5 Newton per mm square. So you need to find out the total extension, how much extension has happened because of the application of this 1000 kilonewtons. Now we know that by using principle of superposition, the total extension can be taken as the extension of individual sections, section 1 plus section 2 plus section 3 plus section 4 plus section 5. But before calculating the extension of sections, individual sections, we need to know the free body diagram, how much actual load is acting. Okay, free body diagram we should know. See, if you observe here, when you observe this total bar, there is 1000 kilonewtons applied this side, and there is no other internal forces applied. There are no other internal forces. Means there is nothing is applied at the internal, means along the length. Okay, except the extreme points, nothing is applied in between. So what you can do is, when you draw the free body diagram, if this side is 1000 kilonewtons, same internal force will be there at this side, because nothing is applied here. The same will be there. Okay, so when you draw the free body diagram, FBD, okay, so for section 1, so you have, this is 1000 kilonewtons, the same force will be the internal force. This is the internal force, 1000 kilonewtons, right? So internal force at this point. Now if you take the extension in section 1, it will be PL by AE, right? So what is P? P is 1000, okay, into 10 cube, because I am converting kilonewtons into newtons. 1000, what is the length here? 0.6 meters, so I am just converting into mm. So always you make sure Newton per mm square, because you have mm, right? So PL by A. A means area, pi by 4, D square, it is D diameter is 100 mm square, into Young's modulus is 2 into 10 power 5. So when you are taking these values, you make sure that here Young's modulus is Newton per mm square. So this P also should be in newtons, L is all, L should be in mm, A should be in mm square. So then you can take it right, you can take directly E as a Newton per mm square. So this is extension in section 1. Similarly, if you take in section 2, so section 2 is this one, right? So the length of this is 0.4 and the diameter is 70 mm, and there is nothing is there here, there is no external force is applied, so the same internal force 1000 kilonewtons will be there this side and this side. Okay, this side and this side, the same internal force will be there. These are the internal forces at this point. Okay, so when you just cut it, this side 1000 will be there and this side so 1000 will be there. Okay, so that internal forces, these are the internal forces which is acting at these 2 points. So the extension in section 2 will be PL by AE. So I can write down PL2 by A2E. Here it is PL1 A1E, and this is also equal to 1000 into 10 cube into 0.4 into 1000 divided by pi by 4. Its diameter is it is 70 square into 2 into 10 power 5. Okay, this is for section 2. Similarly, if you observe here, so for this section, everything is, the load is same. So PL by, so load is same, P by E is same. So only change is L1 A1, it is changing. So see, if there are if there are no internal forces, no, I mean externally applied along in between, if there are no forces are applied in between, then what you can do is no need to draw the free body diagram for all the members. You can say the same load will be applied for all the internal members. So the total extension according to principle of superposition, total extension can be written as P L1 by A1E plus P L2 by A2E plus P L3 by A3E plus P L4 by A4E plus P L5 by A5E. So this is how you can take the common P by E and you can write down L1 by A1 plus L2 by A2 plus L3 by A3 plus L4 by A4 plus L5 by A5, because P and E are same load will be there. So L1 by A1 plus L2 by A2 plus L3 by A3 plus L4 by A4, L5 by A5. Now you calculate A1, A2, A3, A4, A5 and substitute in this. Okay, so what is A1? A1 is nothing but here field cross section area. There are 5 sections, 1, 2, 3, 4, 5, right? So like this. But if you observe here, these two are same and these two are same. So what I can do is here I can write down as 2 times. So these 2 sections I can write down 2 times. These 2 sections I can write down 2 times. Isn't it? So remaining this thing will be left out. So I'm just writing here. P will be 1000 into 10 cube divided by Young's modulus 2 into 10 power 5 into, so what is the length? So it is 600 plus 600 divided by you can say pi by 4 100 square plus, so it is 2 times. I'm writing 600 by 600, and here also 700 plus 700 divided by pi by 4 pi by 4 70 whole square plus L5. L5 is 500 divided by pi by 4. That length will be 90 whole square. Okay, so this is how you can write down, and you calculate the final extension, and you calculate and tell me the answer for this. Okay, so this is one problem. So another problem, let us another problem. A steel bar of variable section is subjected to forces as shown. Take E equal to 205 kilonewton per meter square. So you have to observe these units, whether it is a meter square or mm square. Accordingly, you have to take the values of area and length. Determine the total elongation of the bar. Okay, so this is the diagram. So there is a 55 kilonewtons applied. This side is 45 kilonewtons is applied, and this side it is 20, and this side it is 30. The diameter is 30 mm, and here it is also 35, and here it is also 30 mm. Okay, it is a diameter, so it means that it is circular cross section. It will mention whether it is a diameter or rectangular cross section or square sections. It will be mentioned in the problem. Okay, so here in the diagram it is mentioned 30 mm dia, or sometimes it is represented with a symbol called phi. It is the representing of diameter of a rod by using a symbol phi. So the length of the section 1 is 1 meter, so it is 1.2 meter. It is also 1 meter. So this is the length. Now we have to find out the total extension, elongation of the bar, total change in length. So here if you observe here, so there are different external load applied. One side is 45, another side is 55, and there are internally in between also external load is applied. One is 30 and another is 20. So you need to draw the freeboard diagram of each member, each section separately, and then you have to calculate the total each member elongation separately, and you add total elongation. Okay, so let's draw the freeboard diagram. But before drawing, I am calculating area of the bar 1 equal to pi by 4 d square. It is pi by 4 30 square, and keep it is in mm square. Area 2 equal to pi by 4 35 square. A3 equal to pi by 4 30 square. Area of the each member. Similarly, length L1 equal to 1 meter, so you convert into mm, 1000 mm. L2 equal to 1200 mm. L3 equal to 100 mm. Okay, now draw the free body diagrams. Free body diagrams. So the free body diagram of section 1, first section I am taking, section 1. So you draw the free body diagram. So here I am just drawing the free body diagram of section 1. Now how much is the load is applied this side, left hand side, 45 kilonewtons, right? So in order to keep this under equilibrium, this member, this side is also the same load will be applied. Okay, but when you see here, here it is not the same, 20 newtons. Externally there is a 20 newtons which is applied, right? So So you do one small trick here. See, there should be same load which is applied, right? So how you will take the same load here? What you do is you just apply 45 this side and 45 this side. So this is not going to change the physics of the column when you have applied 45 this side and 45 this side. Now you take this 45 for the free body diagram of section 1. So this is 45. So this is the internal force 45 which should be there in order to keep this section 1 under equilibrium. So now you strike off this because this is already you applied. Okay, this load is already applied, you strike off this, and there is a 45 newtons which is left over here, and there is a 20 kilonewtons which is already applied load, and these are the internally which will be there on the molecule. Okay, at the molecule, at the intersections, so resisting forces will be there. These are the resisting forces 45 this side and 45 this side. So when you cut it, you will see this 45. Otherwise these two will be cancel each other, and 20 will be there. Okay, so next I told you, right, don't go to this section. Next go to this section, extreme section. So section 3 free body diagram. Section 3. So what is applied load? 55. Applied. Now this side also same 55 will be there. Okay, but here what you do is you just add 55 this side, 55 this side. Now take this 55. Okay, now you strike off here, take this 55 and you apply here. Okay, so this is the 55 kilonewtons, 55 kilonewtons. This is free body diagram. Now go to the section 2. Now go to section 2. So in section 2, you see what are the leftover forces here. We just mentioned here, section 2. So leftover forces will be 45, 20, 45 and 20, and this side 55, 30, 55, 30. So what is the resultant here? Resultant forces, resultant this side will be 45 minus 20 equal to 25. This side 20 will be there, and here also resultant will be 55 minus 30, 25 will be. Okay, so the free body diagram for this bar will be this side 25 and this side 25, and you have to mention the arrow mark correctly because the resultant will be 45 minus 20 and 55 minus 30, so it is 25, 25. Right? So now the next step, after drawing the free body diagram, now you have to check whether when you combine these three, you have to get the given bar. So when you combine this and this, so this side is 45, this side is, sorry, when you combine section 1 and section 2, this side is 25, this side is 45. So 45 minus 25, so remaining 20 will be there. So 20 which is there, applied. So this side also, section 2, 25 this side is there, section 2, and section 3 this is 55, so 55 minus 25, so 30 will be there, so this is 30. Okay, now the total extension, in order to find out the total extension in bar equal to extension in bar 1 plus extension in bar 2 plus extension in bar 3. So what you do is extension equal to P1 L1 by A1 E plus P2 L2 by A2 E plus P3 L3 by A3 E. So now P1 will be, for first one, 45,000 into L1 is 1000 divided by A1 pi by 4 D square into E 205. You see here when you mention it is in Newton and mm, this also should be in Newton and mm, and 205 is given as a kilonewton per meter square, right? And you have to convert it. So 1 kilonewton per meter square equal to 1000 Newton per, and here it is 10 power 6 mm square. So this will equal to 10 power minus 3 Newton per mm square. So 1 kilonewton per meter square equal to 10 power minus 3 Newton per mm square. Okay, so we have to convert it. So 205 into, you have to mention Newton per mm square, 205 into 10 power minus 3 plus P2 will be, section 2 is 25,000 into length is 1200 divided by A2 pi by 4 35 whole square into 205 into 10 power minus 3 plus P3 is 55,000 into length is 1000 divided by pi by 4 into 205 into 10 power minus 3. So this is how you can calculate, and you can tell me the answer after calculating all this. Okay. So this is how you can calculate, and I will give you one problem for assignment. Another problem, example 2.5 from the same book. Okay. So remember, ABCD is subjected to point loads P1, P2, P3 and P4 as shown. So calculate the force P2 necessary for equilibrium. If P1 equal to 10 kilonewtons, P3 equal to 40 kilonewtons and P4 equal to 16 kilonewtons. Take Young's modulus equal to 2.05 into 10 power 5 Newton per mm square. Determine the total elongation of the member. Okay, so this is the problem, and this is the diagram which is given. So this is P4, P1, P2, P3. This is 25 mm diameter, 50, and this is 30, and this is 1000, 600, 800. Okay, so and these are the points A, B, C, D. Okay, these are the forces. So see here, a member ABCD is subject to point loads P1, P2, P3, P4. These are the external applied loads, but the member is under equilibrium. So out of this P1, P2, P3, P4, he has given P1, P3, P1, P3 and P4 is given, right? And we don't know this P2. See, if this member is under equilibrium, it means that the total forces, if you add all these forces, okay, by taking the sign convention, it should become 0. It should become 0 because there should not be any resultant force which should act on the member. So under equilibrium, so see here, if you see, this P1 is this side and this is this side and this is this side and this is this side. Some two forces are, if you see, this force and this force are acting left side, and this force and this force are acting right side. So under equilibrium, left side forces and right side forces should be equal to each other, then only it will be cancel each other. So P1 plus P3 should be equal to P2 plus P4. So if both this side forces and this side forces are equal, then it is under equilibrium. So out of this P1, P2, P3, P4, P1 is given 10 plus P3 is 40 equal to P2, we don't know, P4 is 16. So it means that P2 equal to 50 minus 16, that equal to 34 kilonewtons. And the direction is you are getting P2 equal 34 kilonewtons, and the direction is in the side of P1, P3, right? So sorry, actually this is in this direction, because P2 and P4 are the same in this direction, right? So these are the 34, these are the magnitude and direction of load P2. Okay, now you have calculated P2, you know P1, P2, P3, P4. Now you draw the free body diagram of each member separately and then calculate the total elongation. So I'll just draw the free body diagram separately. Free body diagram of section 1. Section 1. So you take the section 1. So what is the P1 force which is acting? P1 is given as 10 newtons, 10 kilonewtons. The same 10 kilonewtons will be there this side also. This is the internal force. Remember, this is external, this is internal force, because when you are cutting this section, there will be internal resistance force which are acting. So that's what we are representing. So what you do here, here when you cut this section, there are two internal forces. This side will be there 10, this side will be there 10.